All right, so yesterday in lab we started going over Lewis structures and molecular shapes. And we talked a little bit about VSEPR theory in class yesterday. That's valence shell electron pair repulsion. And we basically said that electrons want to be as far apart from one another as possible. And we're only looking at a handful of different shapes. We're not going to look at the more complicated ones. And so, for example, we saw molecules that were linear, trigonal planar, bent, tetrahedral, and trigonal pyramidal. And that's what your project was yesterday. I did want to show you something else, too, if you are struggling with this. I've got a link on the top here for a PhET simulation. So if you open up OneNote, you can pull that link up. And what you can do is when you open it, you can switch between models and real molecules. And for example, this is water right here, and you can actually rotate it around. And then on the bottom, you can actually see the molecular geometry and the electronic geometry. So for example, water has 2 bonded atoms and 2 lone pairs. So its electronic geometry is tetrahedral. But to be more descriptive, we can describe the molecular geometry, which in this case is going to be bent. Then you can go to the drop-down menu. So maybe we do something like CO2. Central one's carbon, and then we've got 2 oxygen atoms connected through double bonds. In this case, the molecular and electronic geometry are both linear. So you can play around with that. The model one is kind of neat because you can actually start adding in new bonds and actually build or remove a molecule. So maybe you do something like that and you can rotate it around and then say, what's the electronic geometry for that? So it's a kind of clever tool if you just want to practice building models without a model kit. All right. Also yesterday in class, we started talking about polarity. And the big thing to take away from this is when you draw the Lewis structure, you want to convert that to the 3D shape. So in this example, we have BF3. We converted that to the trigonal planar shape. And in this case, we know because it's trigonal planar that there's no net dipole. All of those individual polar bonds cancel out. However, with something like NF3, you've got that lone pair. That changes the overall 3-dimensional shape to trigonal pyramidal. That means that there isn't a canceling out of all the dipoles, and the net dipole is pointed down. So this would be an example of a polar molecule. Are there any questions with this? I know we went through it pretty quick yesterday.
Are trigonal pyramidals always going to have net dipole?
Trigonal pyramidals usually have a net dipole, unless the individual dipoles are so small. Like let's say it's a difference of less than 0.5 on that table, then you would say it's really not that polar. Yep.
For the exam, we need to know that chart that you give us.
Yeah, I want you to know the shapes of all the various molecules with the exception of those bottom 2 rows that got more complicated. You'll learn those if you take more chemistry. All right, so now what we need to do is learn how to name all of these. And I've got a pretty funny article I like to show. This was in the AP. In California, it said city officials were so concerned about the potentially dangerous properties of dihydrogen monoxide that they considered banning foam cups after they learned the chemical was used in their production. Then they learned to their chagrin that dihydrogen monoxide, H2O for short, is a scientific term for water. It's embarrassing, said the city manager. So dihydrogen monoxide is the true chemical name for water. Most people call it water, but it is pretty funny. I see this almost every year where some city official does this as a prank and somebody takes it seriously. I saw one the other year where it said, there's this really dangerous chemical that's in our community, and if you inhale it, you'll actually die. And it's like, yeah, if you inhale water, you'll die. It doesn't mean it's dangerous. So it's important to know how to name molecules. So I'll show you some simple rules for naming molecules. And you have to know prefixes in order to name these molecules. And right now we're only focusing on covalent compounds, not ionic. So I really want to highlight this is only true for covalent compounds. So let's make a list of prefixes. And their corresponding number on the right-hand side. So for example, we'll just go down and fill in some numbers. All right, what do you think the prefix is for 1? Mono, exactly. kind of like a monocle would be or one lens for one eye, not for both. All right, what about for two? Di. This one's a little bit confusing. Sometimes people say, well, why isn't it bi, like bicycle? I don't know, they just chose di. All right, what about three? Tri. That's not bad. What about four? Tetra. It's not quad, unfortunately. So these do sometimes differ from what we throw out as like a four-wheeled truck, you'd call it a quad, something like that. But in this case, we would say tetra. What about five? Be penta. What about six? Does anybody know that one? What do you call a six-sided shape? Hexagon. What about seven? Seven-sided shape? Hepta. And then we can always go further. We'll go out to 10 and then kind of stop at 10. There's numbers going much farther than that. What do you think 8 is? Octa. 9 is nona. And 10 is deca. So I do want you to know these prefixes. Most of them are fairly intuitive. The ones that people mess up are di and bi. You want to use di, not bi. And then same thing with the one for tetra. Sometimes students will write down quad. You always want to use tetra rather than quad. All right, so let's take a look at some of these. And I am going to put a note. You don't need a prefix if mono comes first. Actually, I'll just write, don't use mono if it comes first. All right, so let's do some examples. And we'll do some common ones that you might be familiar with. CO2. We would first name it carbon, and then the oxygen, because there's two of them, would be di. So it'd be carbon dioxide. So in this case, the di clearly indicates that we have two oxygens. And in addition to that, you change the suffix to an IDE suffix. Does that make sense? It's pretty easy to remember that because we're pretty used to hearing about carbon dioxide. All right, this is very different than CO. What would CO be? Carbon monoxide. So just like before, we keep the IDE suffix. However, because there's only one, we put in mono at the beginning. Some people get confused and they say, should it be two O's in between? So monoxide. Honestly, they just changed the spelling so that it flows better, so it'd be monoxide here. All right, let's try a harder one. Let's try N2O4. What would this be called? Got two nitrogens, so be di-nitrogen. You don't need the IDE suffix for the first one. So di-nitrogen indicates that you've got two of them. And then what would the last part be? Tetraoxide. Oop. So we've got the IDE suffix still, and we've thrown in a tetra. If you notice with the carbon dioxide and carbon monoxide, we didn't say monocarbon dioxide because that would have put mono first. It's redundant. You don't need to include that. If you don't see mono for your first one, it's implied that there's only one. Okay, let's do a couple more. Let's do P4S3. Give me a thumbs up if you think you agree with your neighbor. Would it be quad phosphorus? No. People would look at you funny if you said quad phosphorus. What would be better? Tetraphosphorus. Okay, so we'll fill that in. Be tetraphosphorus. And then what would the last part be? Trisulfur or sulfide? Trisulfide. There we go. So we want to keep that IDE suffix, and we have the tri to indicate that there's 3. Does that make sense? Do you guys want to try a few more? What's that? PF5. All right, let's do that one. PF5. Let's try to name this one. Would it be monophosphorus? Nope, you don't need the mono, so just be phosphorus. And then what would the last part be? Pentaoxide. Oftentimes that looks funny, so you just say pentoxide. Like I said, they change the spelling sometimes by a letter or two just to make it flow off your tongue better. So in this case, it'd be phosphorus pentoxide. Make sense?
Why does it become oxide?
Oh, sorry. Holy cow.
Yeah, I was like,
This is good that I keep you guys around. You keep me honest. Pentafluoride. Thank you. There we go. That looks way better. So it'd be phosphorus pentafluoride. All right, so the main thing to remember is this only works for covalent compounds. How do we identify a covalent compound versus an ionic compound? Does anybody remember? Covalent compounds are always between non-metals as far as we're concerned. So if you notice, all of these are non-metals. And so we want to use this naming system anytime you have non-metals bonded together like that. There are some exceptions, and we'll cover that later. There are some ionic compounds that exclusively contain non-metals, but they're more the exception than the norm. All right, so now we got to switch gears and we got to talk about ionic bonds. We spent a fair amount of time on covalent bonds. And let's first define the difference. So we said covalent bonds. What happens with the electrons in a covalent bond? Yeah, they share electrons. And ionic bonds are different. They don't share electrons. What happens in an ionic bond? Yeah, a transfer of electrons. And quite often this occurs between a metal and a non-metal. All right, I do have a good video I wanted to show you really quick. So let's pull up this YouTube video. And we can see what happens during the transfer of electrons. Oh, shoot. Oh, never mind. This is a different one. Another dog one. I forgot it was up here.
Chemical bonds are when four atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in the chemical bond are called valence electrons. These are electrons that are found in an atom's outer shell. Let's take a look at the types of chemical bonds that can be formed between atoms.
Oh.
An ionic bond is when one of the atoms loses an electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion.
Not a dog ion. It's a cat ion.
And the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There's also what's called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair
I love those videos. They never get old. All right, so going back, covalent bonds, you're sharing electrons. There's two types, the nonpolar where they're shared evenly, the polar where they're shared unevenly. And that's way different than an ionic bond where you actually move electrons from one atom to another. So let's take a look at the classic example. And down here we've got sodium and chlorine. And if we think about sodium as a neutral molecule, or a neutral atom, I should say, how many valence electrons does it have? It's in group 1A. Should just have one, right? Chlorine, as a neutral element, how many electrons should it have? 7. And if you remember, atoms want to have an octet of electrons around them. So in this case, chlorine's not happy. It only has 7 electrons. So what it's going to do is it's going to yank away an electron from the sodium and steal it. So when this reaction occurs, you end up with sodium that lost an electron. So what sort of charge will it have? Have to be positive, right? Because it lost an electron with the negative charge. So sodium would become positive. And then chlorine over here stole the electron from sodium. So what charge will it have? Negative. Okay, so I'm just going to circle these. The main thing that occurs in an ionic compound is you have an attraction between a positively charged cation and a negatively charged anion. And these typically form these big three-dimensional lattice networks, almost like a brick wall, where they just like to snuggle up to the opposite charge in this big three-dimensional network. All right, this reaction is actually pretty cool to watch, so I pulled up a video of it. Let's see what happens when you react sodium with chlorine. Oh, shoot.
Reaction, once it activates, you try to drop some water with the pipette to start the reaction.
So he's got chlorine gas in there and then sodium metal.
There it is. The white smoke you see is sodium chloride solid, alkaline. So that white smoke is the presence of sodium chloride that we made.
So it's typically a very violent reaction when you do this transfer of electrons. Does anybody know what sodium chloride is often referred to as? Salt. It's table salt. So it's a really common ionic compound you see in your day-to-day life. And it can be made this way. However, most of the time the salt we eat is just derived from dried out ocean water. Yep. Either one.
How would you put this on a Lewis dot circle? Because it's stolen the electron, do you put a dash in between, or?
No, that's a really good question. So the question was, how do you draw this with Lewis dot structures? You don't draw them with a bond between them because they're not sharing any electrons. So if you do draw them, you want to draw them as separate cations and anions that are just next to one another, but not attached to one another. Does that make sense?
Okay.
Yeah. And was your question the same?
Oddly enough, yes.
All right, there we go. So let's take a look at some nomenclature or some naming here. The generic term ion is an atom or molecule with a charge. It could be any charge, positive, negative, doesn't matter. An ion is just something that has a charge associated with it, right? And from this, you can split it up into two categories. If it has a positive charge, is that the cation or the anion? Cation. Okay, so that's the cation. The way I remember this, I know this is cheesy, but there's a T in the positive charge, there's a T in the cation, and there's a similar looking plus in the plus symbol. So you can kind of say positive cation, the positive charge, all have that matching symbol. Versus a negative charge. This is our anion. And so, unfortunately, you don't have that combo of the positive, the negative matching anything in there. So cation has the T in there, and it matches the positive charge. Make sense? All right. So let's try filling out a table again, and we're just going to do a little bit of review. We'll do protons, neutrons, electrons, charge, and then I'll do cat or anion over here. We've got a bunch of columns, and then I'll give you some elements, and I want you to help me fill out this table. So the first one, I've got 23 Na. Next one, I've got 23 Na plus. And the last one, I've got 35 Cl minus. So I'll give you a minute to fill out this table. But this could be something that shows up on the next exam or the final exam. All right, let's try to do this as a class. Let's start with the first one, sodium 23. How many protons does sodium always have? 11. Doesn't matter if it's cation or anion, so I'm just going to go ahead and put 11 down here too, right? All right, based on that, how many neutrons must sodium 23 have? Would it be 11 neutrons?
That's the neutral charge.
Neutrons don't have a charge, right? Neutrons are neutral. So 23 minus 11 means we have 12 neutrons, right? All right, in this case, there's no charge shown for that top one, so how many electrons must it have? 11. What must its charge be? 0 or neutral, so I'll just write 0. Is it a cation or anion? It's neither. It's non-ionic. All right, sodium 23 has a cation. How many neutrons does it have? Still 12, right? Because neutrons don't have a charge. And we know the mass number is 23, so 11 minus 23 is still going to be 12. How many electrons this time? 10, exactly. We lost an electron, which is giving it a positive charge. So it would be 1 plus. Would this be a cation or anion? Cation, it's got the T there. All right, and then chlorine, what's its atomic number? How many protons does it have? 17. How many neutrons must it have? 18. How many electrons must it have if it's negative? 18, right? Because it has one more electron than proton. That gives it a -1 charge, right? So would this be an anion or cation? Anion. There we go. So we can start adding a little bit to those tables that we've been working on. It is interesting too, if you remember back to the law of definite proportions, what did that state? Does anybody remember? It was that molecules and compounds are made up of a fixed ratio of atoms. I'm just going to abbreviate this. And this is actually true for both covalent compounds and ionic compounds, but let's take a look at how they differ. So with covalent compounds, a simple example we could look at would be something like water. So let's say we've got a big glass of water. That means we have a bunch of these water molecules floating around, right? And in this case, there's a 2-to-1 ratio of hydrogen to oxygen. Right? It doesn't matter how much water you have. It's always going to be a 2-to-1 ratio as long as it's only water, right? Let's think about ionic compounds. So with ionic compounds, let's say we've got something like sodium plus chlorine. It'll be sodium chloride. We said that if you combine these together, the sodium cation plus a chlorine anion, what you end up getting is almost a 3-dimensional network that looks kind of like this, where you've got alternating sodium chlorine, sodium chlorine. And then underneath the sodium, you might have another chlorine, and then another sodium, and then another chlorine, and then another sodium. And then we can keep on doing this until your hand falls off. But I'll stop after this row. But really, it's a big 3D network of stacking and alternating cations and anions. So you guys kind of see that? So the big thing to note is that it's a 3D network. Of cations and anions. However, the ratio is still 1 sodium to 1 chlorine. So it's still a set ratio of defined proportions. So the law of definite proportions applies to both covalent compounds and ionic compounds, but they're very, very different in how they behave, right? Covalent compounds can kind of float around. Ionic compounds are like a brick wall. They just don't move. All right? And the reason they stack that way, like I said, is opposite charges are attracted to one another, so they want to arrange themselves around opposite charges. So if you're a cation, you want to be surrounded by anions and so on. To look at this using a 3D picture, you can see down here, we've got sodium cations and chloride anions. Sodium's much smaller than chlorine, so it's kind of represented by that small blue sphere. And then if you zoom out, you get this 3-dimensional packing network. And if you zoom out even further and look at salt crystals under a microscope, you can actually see that they're cubes. So if you ever get a chance, let's say in a biology lab, take a salt crystal, put it under there. It's a bunch of small cubes. It's really easy to identify salt that way. But that's due to the packing network of sodium and chlorine. Does that make sense? Okay. Now what we need to do is learn how to predict charges. And I'll show you a few tricks that'll make life easier. And predicting ionic charges follows some simple trends. The main thing to remember is that main group atoms will gain or lose electrons in order to have an octet. So that they have an octet of an electrons. So the example that we saw previously was with sodium and chlorine. We said that sodium had 1 electron, chlorine had 7 electrons, and we took this 1 electron from sodium, we gave it to chlorine. Whoops. And when we did that, sodium down here now has no electrons, but that's also about the same as having an octet, right? So sodium is now positive, and chlorine, we said, now has 8 electrons, making it negative, but it's happy now because it has an octet. That's essentially all I mean by that, is you want to transfer them so that the atoms are happy with 8 electrons around them. If you look at the periodic table, it's pretty easy to figure out what's going on. That means in group 1A, anytime you have one valence electron, it likes to give those up. So typically group 1A elements, when they're in ionic compounds, will have a +1 charge. Group 2A, they have 2 valence electrons, so when they participate in ionic bonding, they have a +2 charge. If we go over to group 3A, these like to have a +3 charge. 4A, it's kind of in between. It doesn't necessarily want to gain or lose electrons, so typically group 4A isn't involved in ionic bonding for the most part. And then when we get over to 5A, it would rather steal electrons than give up all 5 of its electrons. So typically these are -3. And then if we go over, it's -2, -1. And why don't the noble gases have charges? Yeah, they already have an octet. So you can use this as a rough guide. So kind of count up, +1, +2, +3, skip 4, and then -3, -2, -1. What you may notice is this middle block, I kind of skipped over. The charges for transition metals tend to vary a fair amount. And we're going to talk about that. All right. So let's take a look at a pretty simple trend here. The key point I want you to remember is your charges must cancel. So for example, with sodium and chlorine, we've got a +1 and a -1. That means they cancel out. That means we can form an ionic compound from this, and it is exactly a 1-to-1 ratio, so we would represent this as NaCl. Does that make sense? Let's look at some harder ones, though. So for this practice one, what is the salt that forms? Salt is another word for ionic compound. When potassium reacts with oxygen, so I'll give you a minute to think about this, but let's first start by drawing a neutral potassium molecule. How many valence electrons will potassium have? 1. All right, and then we know it's reacting with oxygen. How many valence electrons does oxygen have? Should have 6, right? Oops, I'm cheating. There we go. So if we look at this and try to do the same thing that we did with sodium and chlorine, we could donate one of those electrons from potassium and give it up to oxygen, but is it happy? No, why not? Oxygen would still only have 7. So what do you think a solution could be? Find another potassium, absolutely. So let's say we have a second potassium. We can give 2 of those over. And now we've got the potassium here. It's got a positive charge. The second potassium also gave up its electron, so it has a positive charge. And then oxygen over here now is happy because it has an octet of electrons, but what charge will it have? 2 negative, exactly. So I'll just circle that. If we think about the molecular formula for this, what would it be represented as? We've got 2 potassiums. So would we say 2K or K2? K2. So the 2 always goes subscript after the element that it's representing. So it's saying for every 2 potassiums, we would have 1 oxygen. You don't need to include the 1 there. Anytime you don't see a number like that, it's implied. So the molecular formula for this would be K2O. Does that make sense? I'll show you the trick though. draw out the expected ions. So for example, with potassium we know as an ion will always be +1 because it's in group 1A. So I'd say, all right, +1 here. And then oxygen, I'll put that over here. I'm not even going to draw the dots because we're not worried about them right now. Oxygen, when it's ionic, we know is -2, right? If we go up to this table, oxygen, because it's in group 6A, likes to be -2. So you can go ahead and say -2. And then what you do, it's pretty easy, take this number, swap it down over here, then this number, swap it down over there. So for example, by pulling that 2 over, it goes in front of the potassium. And for the oxygen, it'd be 1, but like I said, we normally don't like to draw the 1, it's always implied. So you can use that kind of flip-flop rule in order to predict your ionic formula. Does that make sense? All right, I'll give you one more practice one, and I want you to see if you can solve this with your partner. So what ionic compound forms between magnesium and nitrogen? So see if you can solve this with your neighbor. All right, give me a thumbs up if you think you got it already. A few people? So let's start with the trick one first, and then I'll show how it makes sense using the other method. So magnesium is in group 2A. What charge will magnesium have? +2? So I'll do the trick one and say, all right, that's +2. Nitrogen is in group 5A. What charge will it have? -3? So with that trick, we said the 3 should come down here. The 2 should come over here. So when we mix these together, we'd have Mg3, not -3. And then N2, right? So the 2 went behind the nitrogen now. So we would expect this to be the molecular formula. But let's try to rationalize this using some drawings. So for example, magnesium normally has 2 valence electrons, so I'll go ahead and draw both of those. And we know we've got 3 of them based on the trick that we just did. And we know we have 2 nitrogens. How many valence electrons do nitrogen normally have? 5. So I'll say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we have to figure out how all of this is getting transferred. So for example, this nitrogen on the top needs 3 electrons to have an octet. Okay, we can steal 2 electrons from this first magnesium. However, the third one needs to come from a second magnesium. So I'm going to say, all right, third one comes there. Now we've got an octet of electrons. The bottom nitrogen needs 3 electrons too, so it'll steal 1 from that nitrogen and 2 from that nitrogen. And so when we mix this all together, we've got magnesium with the +2 charge because it lost both electrons, magnesium with a +2 charge, and our third magnesium also has a +2. So we've got 3 of those magnesiums with +2. And then the nitrogens, we've got 2 of them, and each of them gain 3 electrons. So they have complete octets around each of these, which means that each of these would be -3 due to this theft of 3 electrons from each of the magnesiums. Does that make sense? It's also confusing too. Students will ask me, why don't we do nitrogen first, followed by magnesium? It's general convention to always put your cation first. So let's make a note of that too. cations come before anions. And this is true throughout chemistry. It's just the standard way everybody's done it for a while. Does that make sense? All right. Debating whether or not we want to jump into a new topic. Do you guys want to do more practice or get out early?
I feel like we good.
Raise your hand if you want more practice. I'll do one more practice one for those of you that want to see it. The rest of you are welcome to leave. Let's do... Oh man, everyone's staying. This is good. All right, let's do magnesium and sulfur. Figure out what ionic compound occurs when you mix magnesium and sulfur. With the 2 minutes that we have left. So really quickly, we can draw this out. What charge does magnesium normally have? +2 or 2+, either way. And sulfur? 2-. And if we try to do this same thing again, students oftentimes get tempted to write Mg2S2. However, that's not using least common denominators. So what you can do is to simplify this, just write it as MgS and keep least common denominators. And this makes sense too, right, from the picture. We know that magnesium has 2 electrons. We know that sulfur has 6. So really, whoops, forgot one of my electrons. So really easily we can say magnesium can give up both of its electrons to sulfur, and it's a 1-to-1 ratio in order to pair these up with like charges. So you do occasionally run into the situation where you want to swap to least common denominators. Make sense? All right, I'll see you guys tomorrow. We'll do naming with ionic compounds tomorrow.